All right, thanks so much, Kristen. Yeah, so this is probably going to be my last official function as Desk Team 3 lead, since I'll be rotating out, and after from the beginning of November, Max Paul will be the team lead, and Ashu Hu will be the co-lead. So I'm very excited that Jiaxu is going to be the speaker today at this webinar series. Jiaxu started working at Los Alamos National Lab in April or so, and she came from the group of Zheng Lu at the University of Wisconsin at Madison, where she worked on the implementation and the use of these isotope-enabled tracers in POP to study AMOC behavior during the last deglaciation. So go ahead, Jiaxu.
Thank you, Wilbur, for your introduction. And can you hear me clearly?
Yes, we can.
Hi. Okay. Cool. Sounds good. So I'm Jiaxu Zhang, and today I'm going to present mostly my PhD work. This piece of work has been published in PNAS just 2 days ago. So you're welcome to download the paper and take a read. And if you have questions, just send me email at jiaxu@lano.gov, and I will be happy to answer these questions. So during the last deglaciation, which is about 19 to 11,000 years ago, the Earth started to warm up from the last glacial maximum all the way to Holocene. But this warming course was not smooth and steady. That it was punctuated by quite a few abruptly and warming events, which are linked mostly to the AMOC changes. One of them is called Henrik Stadial 1, which is about 17.5 thousand years ago. And during this period, there is a great amount of fresh water dumped into the North Atlantic, and there is cooling in the north and warming in the south, and which is known as the bipolar seesaw effect. However, for the deep ocean, what happened during that time is completely a mystery. So how about the circulation? How was the temperature changed, and how the water masses changed? So these are just all open questions. So why do we care so much about the deep circulation and the deep water masses? One of the reasons is that during the last glacial maximum, there is a great amount of carbon stored in the deep ocean. So when the deglaciation happens, the CO2 can be released into the atmosphere and warms the whole Earth. So how the deep ocean circulation changed can affect how we understand how the CO2 was released. Second, right after this HS1 event, there was abrupt body envelope warming event. So people have been arguing that this HS1 has a precondition for this warming event and store heat in the deep ocean. And finally, so how well the model simulates the past is a good test for the model fidelity for future climate predictions. So in order to understand the deglaciation, one way is to take a look at the δ18 records. So this purple curve shows a δ18 record at a core site in the deep North Atlantic at 3,000 meter depth. So you see that. So here is the last glacial maximum, and the y-axis is flipped. This is high value here and low value here. So we see that during HS1, there is a very rapid decrease of this δ18 record. And why it is decreased? This is the hypothesis that people raised. It is called the southern source hypothesis. So during HS1, in the surface, there's cooling and warming at the surface. And because of the reduced AMOC, there is also reduced NADW production. In response to this, there is a chance for the AABW to get enhanced and invade all the way into the North Atlantic, which brings the low O18 water all the way to the core site. So this is something like a oscillation in the deep ocean. However, recently there is another core has been found in the Southern Ocean at 3,700 meter depths, this blue line. So what it shows is that actually in the southern core, the decrease of the δ18 lags the range of the purple line. So what it indicates is that people argue that if this is the case, the water comes from all the way from the south, you expect that the change in the south should lead the purple line, or at least the same time with the purple, instead of be lagged. So based on this record, people raised another hypothesis, saying it is called the northern source hypothesis. It says, although the AMOC was weak during that period, it still maintained a moderate intensity. You know that it can still bring the low O18 water, which is mostly from the fresh water, all the way to the mid depths of North Atlantic and all the way to the south. So these are the competing hypotheses. So what we did is that we want to investigate this problem from a modeling perspective, and we implement the δ18 into the POP2 ocean model. So this is a modern comparison of this implementation. So this is the model results, and upper panel is from GIS observation. So while the model is not perfect, we do have a lot of biases. But the key point is that for the surface, we are able to simulate these high values in the Atlantic and low values in the Southern Ocean and in the Arctic, although the Arctic biases are much bigger. Another important feature is that if you look at the Atlantic zonal mean, what we see is that there is a very obvious feature of the underwater masses based on the δ18. You see the IW, NADW, and AABW. In the model, we see the same thing. So this is very important that the model can resolve these three water masses, and therefore we feel pretty confident, comfortable that we can use it for paleoclimate research. So because this is an ocean alone model, we will need to get some forcing from a coupled model. So the TRIS-21 is the simulation we used. It is a 22,000 year simulation using CCSM3 fully coupled model. So it was a transient simulation forced by soil installation, greenhouse gases, land ice sheet changes, and meltwater fluxes. And these two figures shows the change of the AMOC during the past 22,000 years in TRIS-21. And you can see that this is the AMOC during the glacial maximum, and it started to decrease in response during the HS1 in response to the freshwater input, and almost collapsed during the late HS1. And there is a sudden overshooting of this AMOC during the polyanaeroid warming event. And there is younger layers, and gradually it goes to Holocene. And this shows the intensity of the lower branch. So what we did is we take the monthly history files from the fully coupled simulation, then take the heat flux, the freshwater flux, the sea ice, and the wind stress, all the forcings to force our POP2 ocean load model on a monthly basis. And the green lines shows what do we got in the top two? So you see that we pretty much captured the changes following the AMOC change in the fully covered model, and you see that this rapid decrease of AMOC and then overshooting features during the last glaciation. Okay, so now let's take a look at the de-escalation scenario. So this figure shows the AMOC at the present date, and you see that there is like a strong and healthy upper cell overturning, and the depth can go almost to 3.5 kilometers, and this is the counterclock returning of the low cell. However, during the last glacial maximum, the pattern is quite different. You see that the intensity is still pretty strong for the upper cell, but it's much shallower. So it's almost 1,000 meters shallower compared with present day. And another difference is that there is a very strong abyssal overturning, and there is a basin-wide expansion of the AABW in the deep ocean. During HS1, what we find is that there is a very dramatic decrease of the upper overturning cell, and at the same time, the lower overturning is also decreased. So you can see this decreasing signal. But because the upper cell is even shallower, so although the lower overturning is decreased, but there is a dominant failing of the AABW over the deep ocean. So it leads to the first finding of this work is that during HS1, both the NADW and AABW formation decreased, with the former decreasing much more. Now let's so in this context, let's take a look at how the δ18 was simulated. So this again is the AMOC change, and these dotted lines are what I showed before, the two core sites in the north and the other one in the south. So you see this lead-lag relationship. The solid lines are what we found in the model. So you see that the model did a pretty good job simulating these two curves, and most importantly, you see the lead-lag relationship between these curves. The beauty of the model is that it's very easy for the model to separate the total change into two components: the change of the O18 in the water and the change because of the temperature. So we further separate these two components, and what we see is very interesting. So again, the dots are observations, and the solid lines are the model. So if you look at the water O18, you see that the change of the two core sites are in the same place. So both of them started to decrease during the HS1. However, if you look at the temperature, you see that the North Atlantic started to warm up during HS1, but the Southern Ocean almost no change of the temperature all the way until the BA event. So it leads to the second finding of this work, that the lead-lag relationship is not caused by the water O18 itself. Instead, it's mostly because of the early warming the North Deep Atlantic, but not in the Southern Ocean. So if we look at the bigger picture, may give us a better idea what happened during that time. So on the left is the δ18, and on the right is the temperature. So these are for the Atlantic zonal means. So the upper is for the glacial period, and this is for HS1, late HS1, and the bottom shows the difference. So what we see is that for δ18, there, in response to the freshwater input, the signal is mostly trapped in the northern in the upper ocean of North Atlantic and in the Nordic Seas. And the penetration into the deep ocean is very limited. That's why you see the change at the two core sites are almost the same. However, for temperature, we see that for the surface, there is cooling in the north and warming in the south. So this is a bipolar seesaw as surface. But in the surface, there's overall a warming. But warming in the north, there is a warming core at the mid-depths in the north, which is much deeper than the warming core in the south. And you see this tilted warming signal here. So that's why we see there is a great warming in the north at the northern core site, but there is almost no change or very little change in the south. So next, we want to understand why and how the North Atlantic can be warmed. So the key point to understand this difference is that the deep water formation during the LGM, the location is quite different from what we see at present day. So during the modern time, mostly it's formed in the Nordic Seas, but at the LGM, what we see is that it's located in the subpolar region of North Atlantic, and the depths can reach as deep as 2,000 meter depths. If you look at the change of the maximum mixed layer depths during winter time, you see that at 19 Ka, which corresponds to the starting of the freshwater event, you see a sudden drop of these mixed layer depths, and it started to decrease a little bit, and then there is other sudden drop, and makes it all the way to almost 400 meter depths in the later part of the HS1. And if you compare this to the half-molar diagram of the temperature profile in the northern North Atlantic, what do you see here is that corresponding to these two sudden events, you see the sudden deepening of the isotherms at the 19 K and at 17.3. So there is a deepening, and this is almost very, very consistent with this depth change. And here is a simple schematic figure to show what happened. So during the winter time, there is very strong atmospheric cooling at the ocean surface. So it makes surface water very dense, and there is a sink of this water. So this is the deep convection. And the deep convection brings the warm water up, and it started to suffer another round of cooling, and then it goes down again. But during this freshwater event, the depth of deep convection is much shallower. So the water in the mid-depths has a chance to be kept instead of being brought all the way up to the surface and suffering the cooling. So this is how the mid-depths warming signal can occur. And it can be occurred very suddenly. And next, the question is how this mid-depth warming signal can be transported all the way down to 3,000 meter depths. So we did a heat budget analysis at this core site depths across the time, and different curves shows the different components of heat budget. What we find is that during HS1, there is a very rapid increase of the vertical mixing, which is a very great warming effect. There is also an increase of the vertical advection, which represent the cold upwelling at this depth. So this increase of the vertical mixing overwhelms, well, with a little help of the horizontal mixing, overwhelms the change of the increase of the vertical advection. So this vertical mixing can bring the warmth in at the mid gradually onward to the 3,000 meter depth. And this figure is like a summary of what I showed just now. So the shut-off or the shallowing, gradual shallowing of the deep convection can can cause a sudden change of the intermediate depth temperature and induce a warming signal here. And it is the enhanced diffusive heat flux that brings the down to this core site. In comparison, in the Southern Ocean, I have no time to show all the analysis, but the idea is that because of the reduced of the AEBW, there is reduced the cold advection. So this is a net warming effect. But the eddy activity is so strong that this enhanced eddy advection can compensate this warming effect. So there is almost no change. And this is a short summary of the warming mechanism. And if we compare, so the next question is why the temperature and the δ18 behave so different. The answer is that because temperature is a dynamic tracer, and δ18 mostly in the ocean is a passive tracer. And if you look at the δ18 change, it's brought by the fresh water. So the source of the signal is at the ocean surface. So it takes a long way to bring the signal all the way from the surface to the core side. But for temperature, the temperature cheated. The source of the signal is right at can be suddenly occur in the intermediate depths at around 2,000 meters. So and it's much more. It's much closer to the core side, and the enhanced diffusive heat flux can bring the signal all the way down. So the 4 points I want to make is that the passive tracer response can be very different from the dynamic tracers. So the final slide is a summary. So basically, we show that the isotope-enabled climate models are very useful tools for paleoclimate studies, because previous models we simulate temperatures, salinities, but observations we see all the isotopes like oxygen isotope, carbon isotope, so there is no direct comparison. But now we can simulate the isotopes in the model, and we can compare directly with the observations. So the focus for this study is the debate of the southern and the northern sourced deep water input during the HS1, and we use this new tool to do a transient simulation of the past 22,000 years. And what we found is that first, the ocean circulation scenario is that there is reduced AEBW production and transport with a reduced AMOC. And second, we find that the lead of the northern benthic δ18 is caused mostly by the temperature difference, not by the water weighting. And the third is that we found a new warming mechanism. Basically, we argue that it's mostly induced by the wintertime deep convection retreat, and there is a sudden warming in the mid-depths, and it is brought by the enhanced vertical diffusive heat flux all the way down to the ocean. And finally, I want to make the point that the responses of passive tracers and dynamic tracers can be very different, and we call for caution when you infer this from the δ18 approach when assuming uniform change in deep temperatures. So that's it.
Great. Thank you very much for that excellent presentation.